So,
and now.
Okay.
Good.
Yeah, so thanks a lot for giving me the opportunity to give you a flavor on our experiments of confined matter. So this talk has a fundamental aspect, so where we are interested in the self-assembly of liquid crystals in confinement, in nano-confinement, in tiny pores, in alumina membranes, for example, but also an applied aspect, because our goal is to design, by this confining of liquid crystals in these pores, new materials, in particular towards photonic applications. And this is exemplified here. So basically, the idea is we take alumina membranes, as they are now available also from industry, or you can buy them, where pores form on a self-assembled manner with a hexagonal arrangement in alumina. And then we embed into these pores liquid crystals just by capillary action. So we just imbibe the liquid crystals. And as we saw in the morning already, these liquid crystals, they have a very rich phase transition behavior. It's exemplified here for simple rod-like systems, which form smectic phases or isotropic phase. But you can have also chiral building blocks. Then you can have supramolecular helices. And the idea behind and towards the photonics is now to use or consider the single nanopore as an object which is much smaller than the wavelengths of light. And if you embed then a liquid crystal, you can tune the light-matter interaction on this nanoscale, and this object itself is a meta-atom in the sense of a metamaterial. So then you can basically combine this advent of self-organized nanoporosity in materials with the self-assembly of these building blocks to get a material which has a special optical property that is shown here, where you have an incident beam hitting this membrane, and it is with one polarization of light, and it's split in two, and you can now control this splitting of the polarization. And this is interesting from material science point of view to design materials, but it is also interesting, of course, in terms of what happens with the phase transition behavior and the self-organization behavior in general in these topological and geometrical constraints. And in my talk, I will focus on one peculiar system, and that is a discotic system, which means that the building block is the disk, which is 1.8 nanometer in diameter. It's called HUD6, and it's 0.5 nanometer thick. At high temperature, it forms an isotropic liquid phase, and this phase then transforms via first-order phase transition in a hexagonal arranged phase where you have two-dimensional columnar order, long-range intercolumnar order, and then some one-dimensional order along the channels and along the columns. And what is also interesting then is that along the columns, the electrons are delocalized. So you have PP stacking, which means that you have high one-dimensional charge carrier density or carrier mobility along the columns, which means you have a highly anisotropic conductivity and electrical polarizability. This is, of course, interesting for organic electronics and electro-optics. And you can nicely see that in a melt of this material by X-rays, where you see this intercolumnar order by a relatively sharp red peak. And then there is also a broad peak indicating this short range order within the columns. So the idea is now to put these liquid crystals into the pores, and there, of course, it is very interesting how the liquid crystals anchor at the pore wall. And there it was known that if you have a hydrophilic polar surface, for example, native alumina, you have phase on the surface anchoring, whereas for a hydrophobic unpolar surface, as you can prepare by surface grafting the alumina, you have an edge-on anchoring. So our original goal was to have an arrangement of these columns along the nanopore axis in these alumina pores. Therefore, we thought, okay, let's take hydrophobic pore grafting, and then probably the columns will grow along the channel, as is exemplified here on the left side. So we took hydrophobic channel, imbibed the liquid crystals, and hope to see such an arrangement. And to probe that, there is one very interesting or very suitable method, optical birefringence, which is the method where you take this membrane, you have an incident beam which is linearly polarized, and if you have this kind of arrangement, you will get a splitting of this incident beam in two beams with different propagation speeds. So you have birefringence then also, and they have different speeds, which means you have a retardation of the one beam relative with respect to the other beam. And when the prediction is now, if you have such an arrangement, you would expect what is known a negative birefringent material, where the extraordinary beam is refractive index is a little bit larger than the ordinary refractive index, which is also exemplified here or illustrated here with this indicatrix, which is a prolate indicatrix indicating the refractive index in different directions. So we did such a measurement as a function of time in such a membrane, and that is shown here. So you see the optical birefringence as a function, or the retardation as a function of cooling of these membranes. And you see, instead of going down to negative value, it goes up. And that was quite surprising. So we thought, okay, what happens now? It cannot be this axial arrangement as we hope to observe. It must be something different. And that is now the aspect where the X-rays come in and where they are really very powerful. So we went to the PO8 beamline, took such a membrane and rotated in the beam, and we looked at the sacs and wax patterns as a function of rotation of the membrane, and did kind of a 3D reciprocal space mapping. So we record here the diffraction pattern as a function of orientation of the membrane, and you see at some point you see a 6-fold pattern, and then you see basically a ring. And it turned out that the solution to our problem is that we have edge-on anchoring, but not still this other birefringence, that instead of forming the columns in these systems along the axis, they form also columns, but circular concentric ring columns in the pores. So that's how the liquid crystals solve this confinement problem. But then you can ask yourself, why is this the case? Why do they form this circular concentric ring instead of this axial arrangement in the pores? And there you have to look at the Frank-Ursine defect energies, bending energies in particular for these liquid crystals, or this excess energy which they have to pay if they would like to arrange in these pores. And it turns out for the circular concentric ring configuration, it scales with the logarithm of the diameter per unit length, whereas for the axial arrangement, it scales with d. So that means we are probably in a regime where the logarithm wins, so basically where you get this configuration, but there was some motivation to go to smaller pores where maybe the linear will win, and then you would get the axial arrangement. So we went again to the synchrotron, this time with smaller pores, only 17 nanometers, and the membrane before had pores with 18 nanometers. And indeed, this time we observe a configuration where the intensity and reciprocal space indicates that we have the axial arrangement. However, because you have a huge number of pores illuminated, and therefore you randomize over these orientations here, you have overall a ring and reciprocal space. But we can then very nicely basically understand our scattering pattern. And this is now interesting from application point of view, which means, because it means for large pores, as shown here, you get these prolate indicatrix, you get a positive optical birefringence, whereas if you go to these smaller pores, you get the oblate indicatrix with a negative birefringence. Then we did an additional study where we went even to smaller pores, so where we took silicon and etched channels along the 100 directions. Then we transformed that silicon to silica by thermal oxidation. So the wall is so thin that you can just thermally oxidize it. So it's getting optical transparent, which is of course very interesting for optical applications. Again, we embedded the liquid crystal inside the pore space. And now I would like to ask you to focus on this part, this panel, So here is shown again the optical birefringence as a function of temperature. And you see that up in cooling, you get a sequential increase of the optical birefringence, and on up in heating, a sequential vanishing. And you may already have an idea why this is the case. And the solution is that basically in the very beginning, you have first the formation of the outermost ring here, which has to pay where the molecules have to, or the self-assembly pays the least of bending energy. Then at some point at the lower supercooling, the next ring sets in, formation sets in, and so on until you fill the entire pore space with the sequences of ring, and vice versa. You get also the stepwise or quantized melting, which is completely described or determined by the discreteness of the excess bending energies. You can also do the math on it, and it fits very nicely. And it's a kind of a very interesting system where you have a kind of a quantization of an energy, not of course of an electronic energy, but of a bending energy on the nanoscale, which gives you this quantization of this phase transition. We had during that time also collaboration with people from Göttingen, with Marco Massa and his group, and they could very nicely see this also in Monte Carlo simulations, this formation of these concentric rings, and they then also studied how they form as a function of cooling the system, and you see this stepwise formation of the rings until you form the entire pore, except in the very middle you have always a topological defect, because you cannot fulfill here the boundary condition. So that was some motivation to look in these liquid crystals. And then at some point, Ben Oku actually also found at some point this quantized formation of liquid crystals in confined or semi-confined geometries, rather than liquid solid and liquid vapor interfaces, motivated us to look also at rod-like systems. So we looked at conventional smectic phases in these pores, in particular in the system, which is also interesting from organic electronics, which is C8BBT, but this is not so important. Here you can have many possibilities depending on the anchoring, how these liquid crystals form. And that is again very interesting in terms of transport mechanisms of, for example, electrons in these confined nanorods. And we performed there a couple of experiments at Petra 3, then at NSLS and at ESRF, and we found also that for this system, depending on the anchoring of the pore wall, here is shown a hydrophobic anchoring, and the confinement size, we can switch the system between an arrangement where the smectic layers grow along the direction and also perpendicular to that. And all these experiments have been done with illumination of many pores. So for some of these textures which I showed to you, you may have already questioned, okay, or you are questioning, is this really the single possibility how this arrangement can be, or how is the texture within the single pore? Is it one domain, or are there many domains? Therefore, we started recently to look at these structures also by single pore experiments. We try to illuminate just a single pore, and there we started to cooperate with the group of Christian Schröer, and we performed a couple of experiments at PO6, where we illuminate in transmission the beam, the membrane with a beam which is only 50 nanometers across, so that we have some chances to illuminate just a single pore. And this turned out to be very fruitful in the sense that we could really see in our patterns, in our SAX patterns, single domain states in these channels. And additionally, you see that here a larger recording of such a pattern. We observed also nice speckle patterns, and overall we could, or basically the group of Christian Schröer was able to do also reconstruction of the nanopore array, and we know also exactly now which pore we hit and in which pore we can observe these single domain states, or at least a few domain states, instead of not knowing exactly what happens on a single pore scale, because we usually average over many pores. And this is a direction which we would like to address in the future in more detail. Another aspect is the liquid crystals. They have also a final electrical polarizability, which means you can easily apply electrical field. You know that from your mobile phone, you can change the orientation that makes you the color. And you can do that also in the nanopores. And we for example, we performed now experiments where we sputter tin oxide on both surfaces of these alumina, apply oscillating fields, and look at the rearrangement of the liquid crystals as a function of these oscillating fields. In the future, we would like to do that. So basically, we saw already that this really works. So we recently published this in nanoscale, where we first of all looked at with birefringence how these nematic order forms in the pores, but then we looked also at the different response, which is called the Pockels effect and the Kerr effect, depending whether the response is direct, so with the same frequency or with double frequency in terms of the response function. And this looks very encouraging. In the future, it would be very interesting to look at such a system also with X-rays. Okay, and with this, I would like to thank, first of all, my group and the funding agencies. In Corona time, this is my group now, and I thank also you for listening to me, and yeah, thank you very much.